everyone. Welcome to Learning at 11th Hour. Today, we're going to look at the concept of first order circuits. So, what really are these first order circuits? Circuits that have a capacitor in it in series with a resistance, or circuits that have an inductor in series with a resistance. So, these circuits, and if we are going to subject these circuits to, say, sinusoidal input, or impulse input, or step input, or exponential input, how are they going to respond to these different inputs? The study of these concepts falls under first order circuits. So let's begin. To understand the concept involved behind first order circuits, first we need to familiarize ourselves with the terms transient response and steady state response. So, whenever there is a circuit which is subjected to some change, for example, there is a capacitor which is, say, connected to a source, a voltage source, and this capacitor will therefore be charged. Say this is 10 volts. So the capacitor would get charged to say 10 volts. And after some time, I disconnect it from this circuit and connect it to another circuit having just a resistance, say 5 ohms. Now, this change will not be reflected across the resistor instantly. So to say, the capacitor would begin to discharge through the resistor. Now that it is cut off from the source, it will begin to discharge through the resistor. But it is not going to discharge instantly. It is going to take some time to discharge and then become zero. The charge in the capacitor would become completely zero, but that's going to take some time. And then it is going to reach some steady value, which is zero in this case of discharge. So here we can see two distinct phases happening, right? The first phase is the transient response. The transient response is basically the transitional period during which the branch currents or the voltages, they settle down from some old value to a new one. So this is the transient period. After the transient period arises the steady response. So having said this, we can also say that the transient response can be called as the natural response, and the steady response can be referred to as forced response. Let us now look at the study of discharge of a capacitor through a resistor. So, say in this circuit, we have the capacitor. Now, assume that it is charged to a voltage of V naught, and then we rig up this circuit where we connect this resistor, this switch, and the instant when I close the switch, I turn on my timer. So I'm going to say that at t is equal to 0, the 0th instant, I'm going to push this switch. So that's when my timer begins. But till then, the voltage across the capacitor is going to be V naught. So to say, this is my initial voltage. After which, it starts discharging through the resistor, and so the voltage becomes variable, right? It becomes a variable parameter, and it is going to decrease till it becomes 0. So that parameter is going to be V. So the voltage across the capacitor goes from V naught to 0. So this is going to take some time. So let me call it as T. And through this circuit, now that this is going to act like an energy source, there's going to be current flowing. So it is discharging through the resistor, and the current flowing through the resistor is denoted here by I. So it enters the circuit here and leaves the circuit here. So this is the voltage drop, and across the capacitor, this is the direction of drop. Now, if I assume a clockwise drop direction and apply KVL in this loop, what do I get? So what I get here is V minus I into R is equal to 0, or I can say V is equal to I into R. But what is I over here? I is the current due to the capacitor, which is given as minus C dV by dt. This has been discussed in one of the previous videos. You could go back and check that out. So now that I know the value of I can replace it in this equation. So what do I get? So I'm going to just keep it as this equation and replace it. And I'm going to say V is V minus of minus C dV by dt into R is equal to 0. So the minus goes and we get V plus RC dV by dt is equal to 0. So now I have a linear differential equation over here, and it is going to have two solutions. So the first part of the solution rather is going to be called as the complementary function, and the second part is going to be called as the particular solution. So we see that the complementary function is going to be nothing but the transient response. It's going to represent the transient response of the circuit, whereas the particular solution is going to represent the steady state response of this circuit. Now we can find the solution to this linear differential equation, and we know that uh, the possible way of doing it is where we can replace V with a e power st. Therefore, we can find out dv by dt as s a e power st. Now, let us try to substitute these values over here. So, I had the equation v plus rc dv by dt is 0. So, I can rearrange it as 1 by rc v plus dv by dt equal to 0, where v was a e power st and therefore dv by dt is s a e power st. So on replacing, what we get here is 1 by rc a e power st plus s a e power st is equal to 0. Here, let me take a e power st common, and what I get here is 1 by rc plus s is equal to 0. Now, having obtained this, we can see that we can say s plus 1 by rc is equal to 0. Therefore, s is equal to minus 1 by rc. And we know that v of 0, that is v is a function of time, so it's going to change with time. So v, when t is equal to 0, that is the initial voltage, that is equal to v naught, right? And we can replace the same thing over here and find it out. So if I replace t equal to 0 over here, what do I get? V is equal to a e power s into 0. So that is v is equal to a. So I can say that v naught is nothing but a. So this is the case when t is equal to 0. So now I can find the solution to this. So I can find the expression of v of t, and that would be a e power minus t by rc. So here a is nothing but v naught. I can replace it as v naught e power minus t by rc. So when I take the inverse Laplace of this is what I get. So this is the expression for v of t. From this, I can obtain I, or rather I of t, which is minus c dv by dt. So when I perform that differentiation of v, what I get here is, this is constant, v naught remains, and I have e power minus t by rc. So I'll have minus 1 by rc, and I'll have e power minus t by rc remaining. So now I can cancel out the c, I can remove the minus sign, and what I'm left out with is v naught by r e power minus t by rc. So this is the expression for I of t. Now, if I consider t is equal to rc, say the time instant when t is equal to rc, what happens is e power minus 1 remains over here, because t is rc, rc cancels out, and what I get here is e power minus 1. So is the case over here. So now considering the case where t is rc, so if t is equal to rc, I put it in this equation, what I get is v of t when it is RC is equal to V naught e power of minus 1. So V of t therefore becomes 0.368 times of V naught. Now this value of t is represented by the symbol tau, and it is called as the time constant of this RC circuit. So that is defined as the time taken for the voltage to reach 36% of its maximum value from the maximum value, right? So if I plot a graph, say this is V and this is the time. So it starts from V naught and begins to discharge, and after some period of time it becomes 0. But the time taken for this voltage to reach 0.368 times of V naught, that particular time is called as tau, or the time constant, and it is represented by RC. And for the current also we can do the same thing. If we replace T is equal to RC, so I'll now call it as I of tau is equal to V naught by R e power minus 1. So again, the time taken for the current to reach to 36.8% of its maximum value, that is the time period tau. Okay, and the value of it is given as RC. So again, if I have a plot for the current, it is going to look very similar to this. So here I have V naught by R, that's the maximum value of current, and it discharges, this is the discharge current, and the time taken for it to reach 36.8% of V naught by R. That time is called as tau, given by RC. So this is the time constant of the RC circuit. Let us summarize what we just discussed. So we saw that for an RC circuit where the R and C are in series with each other, and say the capacitor has an initial voltage of some V naught. So the voltage expression when the capacitor discharges through the resistor, given by V of t, is V naught e power minus t by RC. And the current is given by V naught by R e power minus t by RC. Over here, RC is the time constant of this circuit, right? So these are the three things which we can keep in our mind. With that, let us try to solve this problem. So here we have a capacitor of 1 microfarad, and it has been charged to a voltage of 10 volts. So that is why they say when t is less than 0, the voltage across the capacitor is 10 volts. After that, at t is 0, the switch is going to be closed. So before that, so when the switch was open, it was probably connected to a battery and charged to 10 volts. Then the switch was closed, and then it got connected to a resistor whose value is 1 mega ohms. And we are supposed to find out the time constant. We are supposed to find out V of t and V of t for t is equal to 5 seconds. So these are the three things that we need to find out. So we know that here this is the pure case of a capacitor getting discharged through the resistor. So we can say that V of t is nothing but V naught e power minus t by RC. Here, V naught is the initial voltage and it is clearly 10 volts as given in the problem. And RC is the time constant. So tau is equal to RC, which is 1 into 10 power 6, that is 1 mega ohms, into C is 1 microfarad. So 1 into 10 power minus 6. So that leaves us with 1 second, right? So here we have the value of RC as 1 and V naught as 10. So now we get the equation of V of t as 10 e power minus t, because RC is 1. So this is V of t. The time constant as we've obtained is 1 second. We need to now find out the value of V of t for t is equal to 5. So V of 5 rather should be equal to 10 e power minus 5. So when we substitute this value, what we get here is 0.067 volts. So I hope with this example, the concept of discharge of a capacitor through a resistor is clear to you all. So this is a pure case of obtaining the transient response of the circuit. And we'll see more such first order circuits in the upcoming videos. Thank you.